Hello friend, welcome to YouTube channel Electronic. In this video, we will learn common base configuration of BJT. Transistors can be used as an amplifier. Like here in this single stage audio amplifier circuit, the input signal is applied at the base terminal and these biasing resistors provide biasing to the transistor. Hence, we will get amplified output signal from collector terminal. Transistor is a three-terminal device, namely emitter, base and collector. Because of these three terminals, we have three transistor configurations. They are common base, common emitter and common collector configurations respectively. In this video, we will discuss common base configuration of transistor. In common base configuration, base terminal is common for both input and output signal. By looking at the direction of this arrow in emitter terminal of a transistor symbol, we know that this is a NPN transistor. In common base configuration, base terminal is common for input and output. So it is grounded in this configuration. Here, if we apply weak signal in this input side, we will get amplified signal at the output side. This amplification will happen only when we provide proper biasing to this transistor and when the transistor operates in active mode. Every transistor contains two junctions, namely emitter base junction and base collector junction. We need to provide proper biasing to transistor to work it in active mode. Here emitter base junction must be in forward bias. This is a NPN transistor. So voltage at emitter VE must be smaller than voltage at base terminal VB. Alternately, this base collector junction must be reverse biased. So voltage at base VB must be lesser than voltage at collector terminal VC. We can consider transistor as two back-to-back diodes connected in series. Hence, to make a NPN transistor in active mode, VE must be lesser than VB and VB must be lesser than VC. For a PNP transistor, this must be in opposite direction. So what we will do here, we forward bias this emitter base junction via this resistor RE. Here this is a NPN transistor. Emitter is made up of N-type material and base is made up of P-type material. Hence emitter is connected to the negative terminal and base is connected to the positive terminal of the voltage source. We will call this forward bias potential as VEE. Now we will reverse bias the base collector junction via the resistor RC. Here collector is made up of N-type material and base is made up of P-type material. Hence collector is connected to the positive terminal and base is connected to the negative terminal of the voltage source. We will call this reverse bias potential as VCC. Now if we compare the diode and transistor, diode have only one junction and transistor has two junctions. In case of diode, we have forward and reverse VI characteristics, but in case of transistor, we have input characteristic, that is plot between input current IE versus input voltage VBE, and output characteristics, that is plot between output current IC versus output voltage VCB. Now let's find out direction of the currents IE, IB and IC. From the symbol of transistor, we can see the direction of the emitter current IE is like this, and the direction of base and collector currents IB and IC are like this. For a PNP transistor, these current directions are in opposite direction. Please do watch my previous videos to understand direction of these currents. Now here the voltage across base and emitter junctions VB is this potential. If we neglect RE for the sake of simplicity, then VBE equals to VEE. In the same way, voltage across collector and base terminal VCB is this potential. Here also, if we neglect RC for the sake of simplicity, then VCB equals to VCC. Here we cannot write VBE as VEB because base is at higher potential than emitter. So B will come first, then E. In the same way for VCB, because collector is higher potential than base. Please note this. So here we must use VBE and VCB for the input voltage and output voltage respectively. Here we apply Kirchhoff's current law to obtain the relationship between emitter current, base current and collector current. According to KCL, the sum of the entering currents are equal to the sum of the leaving current. In this circuit, we can see that IE is the leaving current and IB and IC are the entering current. So here IE equals to IB plus IC. We will just note down this as first equation. This equation is true when transistor is operating in active mode. Here the collector current IC equals to alpha times IE plus ICO. This ICO is the reverse saturation current. We will rename this reverse saturation current for common base configuration as ICBO. So here we write IC equals to alpha times IE plus ICBO. Here B stands for common base configuration and O stands for open circuit, because here we measure this current when the emitter terminal is open. Here if we compare this IE and ICBO, the emitter current IE is much greater than reverse saturation current ICBO. It is because this reverse saturation current is due to minority charge carriers and this current is very small or negligible. So we can neglect this ICBO. Hence here we can write collector current IC equals to alpha times emitter current IE. Therefore, alpha equals to IC divided by IE. This is very important relation. This alpha is denoted as common base current gain. We already know that gain is equals to output by input. Here IC is the output current, IE is the input current. So alpha is the common base current gain and it is also called as amplification factor, and generally alpha value is in between 0.95 to 0.98. This means 95% to 98% of the emitter current is the collector current. This also shows 5% to 2% of recombination in base. Now base current IB equals to 1 minus alpha times IE. So these are the important relations we must note down. Now let's understand the input and output characteristics. The input characteristics defines the relationship between the input current to the input voltage, that is emitter current IE to the base emitter voltage VBE. Likewise, the output characteristics defines the relationship between output current and output voltage, that is collector current IC and collector base voltage VCB. Here if you see the common base input characteristics, by keeping VBE at x-axis and IE at y-axis, the curves will look like the forward characteristics of the PN junction diode. Here there are three curves for the different values of VCB. That means for drawing each curve, the value of VCB has been kept constant. For active mode operation of transistor, the input side emitter base junction is forward biased and the output side collector base junction is reverse biased. And due to the forward biased input side, these curves looks like forward characteristics of a PN junction diode. If you observe over here, as the value of PCB increases, the emitter current is increasing. So the curve slightly shifts towards the left hand side. The reason behind this is that as the value of PCB increases, the collector base junction gets more and more reverse biased and the width of the depletion region at this junction increases. And due to this, the base region will get narrower. Hence, less input voltage VB is required to forward bias this emitter base junction. Due to this, the curves are shifted towards left hand side. Here we can find input impedance of common base configuration. If we find the slope of this curve, then we can find the input impedance. That means we can say that the input impedance Rin equals to delta VBE divided by delta IE. That is the change in input voltage to the change in input current. If we observe over here, even if there is a small change in the VBE, there will be a huge change in the emitter current. From these input characteristics, we can say that in this configuration, the input impedance is very low. This is expected due to input is forward biased, and in forward biased condition, the resistance of this PN junction is very low. So the input impedance of the common base configuration is very low. Typically, it is in ohms. So similarly, let's understand the output characteristics. Here the collector current IC is the output current, and the voltage between the collector and base terminal VCB is the output voltage. So this output characteristics defines the relationship between output current, that is collector current IC, and the output voltage, that is VCB, when the input parameters are kept constant. Here IC is denoted on y-axis and VCB is on x-axis. The output characteristic curves shows for the fixed values of emitter current. If we change the collector to base voltage, then how the collector current will change. Here the different curves are shown for the different values of the emitter current. As we can see that as the emitter current increases, the collector current is also increases linearly. These curves can be segregated into three regions. First one is the active region, second one the saturation region, and the third one is the cutoff region. We will discuss them one by one. First one, active region. In this region, even if we increase the collector to base voltage VCB, then also the collector current almost remains constant. Here the relationship between the collector current and the emitter current can be given as IC equals to alpha times IE. Here the emitter current IE is the input current and the collector current IC is the output current. The ratio of collector current to emitter current is known as current gain of the common base configuration of the BJT, denoted with alpha. In this configuration, even if we increase the reverse bias voltage VCB, then also there is a marginal increase in the collector current. So we can say that in active region of operation, the collector current acts like a constant current source, and for the fixed value of emitter current, it is almost independent of the collector to base voltage. Due to this type of behavior, this region is used for the amplification, because in this region the collector current only changes with the change in the input current. Now let's talk about the saturation region. Let's observe this region clearly. In this region, as we reduce the value of voltage between collector and base terminals, that is VCB is going to negative, then this collector current starts reducing, because as we remove the reverse bias between collector and base junction, then the electrons which are flowing from emitter to base will not be able to cross this base collector junction. Due to this, the collector current IC starts reducing. Here we can say that both junctions, emitter base and base collector junctions, are forward biased. Hence, here the BJT will operate in saturation region. Now let's understand the third region of operation, that is cutoff region. Here whenever the emitter current is 0, at that time even if we increase the collector to base voltage VCB, then also the collector current almost remains 0. This means whenever we remove the forward bias voltage between the emitter and base terminals, then the emitter current IE will become 0, and in this condition the collector current IC will also almost equals to 0. Here the small collector current which exists is due to minority charge carriers, or we can say that the small collector current is due to the reverse saturation current, because we know that the total collector current ICT equals to IC plus ICO. Here ICO is the reverse saturation current. In common base configuration, if we disconnect this base emitter voltage VBE, the reverse saturation current which is flowing between the collector to base terminal is known as the ICBO. This reverse saturation current is typically in the range of nanoamperes to microamperes. On the other hand, the collector current IC is used to be in the range of milliamperes. So if you observe this graph, in cutoff region, the collector current IC almost appears as 0. Here this reverse saturation saturation current ICBO is depends on the temperature. That means as the temperature increases, this reverse saturation current will also increases. Now the total collector current ICT equals to IC plus ICBO. Here we can write this IC as alpha times IE. So if we represent the total collector current ICT in terms of the emitter current, that will be equals to alpha times IE plus ICBO. Hence this will be the total collector current which is flowing through this circuit. Now let's observe how the input signal is getting amplified in common base configuration of BJT. Here for the sake of simplicity, we didn't consider these DC biasing voltages. Here this input voltage Vin needs to be amplified at the output across the load resistor RL. Let's say In is the input current and IO as the output current. Now as we have discussed earlier, the input impedance in this configuration is very low and typically it is in the range of ohm. Here let's say input impedance or input resistance is equals to 10 ohms. And let's say the input voltage Vin equals to 10 millivolts. So here input current In equals to 10 millivolts divided by 10 ohms. Now here assume that alpha equals to 1. In that case this output current IO is same as the input current In. Because here we know that collector current IC equals to alpha times IE. Here we have assumed that alpha equals to 1. Hence IC equals to IE. This means the output current is same as the input current. Now in common base configuration, the output impedance RO is very high. Typically it is in the range of several kilo ohms. This can be observed in the output characteristic curve. Here in the active region of operation, even if you increase this collector to base voltage VCB, then also the collector current almost remains constant. This means output resistance RO equals to delta VCB by delta IC is very high. Now let's assume output impedance RO equals to 100 kilo ohms and load resistance RL equals to 1 kilo ohms. Now output voltage Vout equals to Iout times RL, that equals to 1 milliamperes into 1 kilo ohms. That gives output voltage Vout as 1 volt. Here the applied input voltage is 10 millivolts, while the output voltage is equals to 100 millivolts. This means the input signal gets amplified by the factor of 100, or in other words we can say that here the voltage gain is equals to 100. So in this way the applied input signal gets amplified in this common base configuration. Here if you observe the current gain, that is the ratio of the collector current to the emitter current, it is less than 1. That means in a common base configuration, instead of current gain is less than 1, it provides very high voltage gain. Typically it is in the range of 100 to 2000. Here in this table, I have summarized the characteristics of common base configuration. Please go through them. Now let's see some applications of common base configuration. This configuration functions as a current buffer because it effectively transfers current from low input impedance source to a high output impedance load. Common base amplifier can be used as an RF amplifier due to its excellent isolation between input and output terminals, which prevents unwanted oscillations. A common base amplifier is often preferred choice for HF oscillator because of its gain and zero phase shift between input and output signals. That's all about common base configuration of BJT. If you have learned from this video, please do mention them in the comment section below. Thanks for watching. If you like this video, please click the like button. Help others to learn by sharing this video. Please subscribe and turn on notifications for more such videos. Have a nice day.